Hello guys, I'm Paul McWhorter from TopTechBoy.com, and we are here with Arduino lesson number 17. In the first 15 lessons we learned the fundamentals of programming the Arduino, and we learned about simple circuit concepts, and now we're starting to look at projects. Cool things that you can do with the simple things you learned in the first 15 lessons. What we're going to learn today is we're going to learn how you can actually measure the speed of sound yourself, and it's not as hard as you might think. You know that these are lessons that I'm putting together for my high school class at El Dorado High School. I'm putting them online so that high school students everywhere can learn this cool stuff if they want to, even if their school doesn't offer engineering classes. You can follow along online with me. The cool thing about this project is measuring the speed of sound is a pretty sophisticated thing, and I would say probably less than one high school students in 1,000 actually design an experiment and execute on measuring the speed of sound themselves. And so if you do this in high school, you're sort of putting yourself in a pretty elite group of 1 out of 1,000. And this is kind of getting you ahead of the rest of the students, and when you get to college, you're already ahead of a whole bunch of people. And so I encourage you to do these things in high school because they're fun, and when you get to college, you're going to be way ahead of everyone else. What we have is we have a simple circuit here, and as we're talking, it is sitting there measuring the speed of sound. It's measuring it at about 786 miles per hour. Let's come over and look and see what the speed of sound really is. It's 77 degrees in this room. I just measured that with a temperature sensor, and so it should be the speed of sound should be 776 miles per hour. 776 miles per hour, and we're measuring it to be 786 miles per hour, almost exactly, just a few percent off. And so that's pretty cool that we're going to be able to measure the speed of sound that accurately. Well, how does this work? This is an ultrasonic sensor. If you go to my website, toptechboy.com, I've got a link where you can pick one up for about $9, so they're not very expensive. There's a lot of really neat projects that you can do with this. The way this sensor works is that when you send it a signal, it sends out a ping, and that ping goes out and hits whatever is in front of it and bounces back. And it measures how long it takes for the ping to go out and come back. Well, if it's an ultrasonic ping, how fast is it traveling? It's a sound wave. It's traveling at the speed of sound. So if you know how far it is to the target, and you know how long it took the ping to get there and get back, then you can calculate the speed of sound. And it's really pretty easy and just takes us a few lines of code. You do have to get this sensor hooked up. So let's take a second and talk about how to get the sensor hooked up. I have it hooked up down here and it's running, but we'll talk about it a little bit more in detail. This is just a picture of a little bit what it looks like up close. But let's go over and look at the schematic of how to hook this thing up. Okay, here we go. So we've got our Arduino. We've got our ultrasonic sensor. The ultrasonic sensor has 4 leads, and they're pretty easy to hook up. Over on the left, we have VCC on the sensor, and we take that to 5 volts on the Arduino. Next up, we have, I believe, is the trigger, the TRIG. The TRIG pin we take to pin 13. That's the pin on the Arduino that will send the signal that tells it to send the ping out. So that's our trigger pin. And then the pin on the sensor that's going to report back to us that travel time, how long it took for the ping to go out and come back. That's the echo pin. The echo pin on the ultrasonic sensor, we come and we hook to pin 11. So pin 11 is the echo pin on the sensor, and then pin 13 on the Arduino goes to the trigger pin on the sensor. And so that's pretty easy to hook up. I show the wires connecting in front of the sensor here so that you can see it, but if you look down here, you really want to hook them in the back of the sensor, and that way those wires don't get in the way of the ping signal that's coming out from this little sensor. So this is just a little easier for you to see where the wires go, but when you hook it up, you probably want to hook it up like this. Okay, so how is this device going to work? The way this device works is it's really pretty simple. That trigger pin, which we said was pin 13, that is what initiates the measurement. And the way you initiate the measurement, you do a digital write low, to that pin 13, you pause, you write it high and you pause, and you write it low and you pause. And when you send that pulse, that little pulse to pin 13, that tells this sensor to send out the ping. It sends out the ping and it comes back. What you get back on the echo pin is a pulse, and the width of that pulse indicates in microseconds how long it took for the ping to go from the sensor, hit the target, and come back. Okay, so now you have some very important information. You have the travel time of the ping in microseconds. Okay, so how would we go through and how would we do the math? Well, what do we know? We know that the speed of, we know that distance is equal to rate times time. Okay, distance is equal to rate times time. We get the time from that echo pin by measuring that pulse width. How do we measure a pulse width on a pin in the Arduino? I think we learned that in lesson number 15. You use the pulse in command. Okay, you use the pulse in command. And I'll go through all this line by line here in a minute, but I'm just kind of describing how it's going to work. Okay, so the speed of sound, we're going to need to know the distance. Well, how do we know the distance? We have a ruler and we measure it down here. So we measure the distance. How do we get the time? Well, the time we measure on that echo pin, right, using the pulse in. So we have distance, and we have the time that it takes for that ping to travel, and so we can calculate the speed of sound. So let's go through that in a little bit more detail now. Okay. In fact, I think at this point I'm probably going to just go ahead and start coding this thing up. I'm going to turn this off. Okay. So let's think about the things that we're going to need here. We're going to need some variables. Well, how many pins are we using? How many digital pins are we using to write? We're using 2 pins. One is the trigger pin that we're going to send commands to, and one is the echo pin that we're going to listen to. So let's start setting those up. We're going to need I'll call it the trig pin. And the trig pin we said was pin 13 because that's how we hooked it up down here. Okay, and that is, let's say that our sensor trig pin is connected to Arduino 13. That makes sense. What else do we have? We have the echo pin. And the echo pin we hook to pin 11. So we'll set that equal to 11. And I say that the sensor echo pin is connected to our Arduino 11. All right. What else are we going to measure? We got to measure that time, right? That ping time, that time that it takes for the ping to go out to the target and come back. Okay. So that ping time is going to be, let's make that a float, okay, because we might want to do some math on that. So let's make that a floating point number or a real number. We'll call that ping time. Okay. And what is that? That is the time for, I need to here, boom, boom, for a comment, time for ping to hit target and return. Okay, that's the ping time. What else are we needing? Well, what are we trying to calculate here? What's the purpose of this? We're calculating the speed of sound, so we need a variable for the speed of sound. So we're going to have float speed of sound, and that we're not going to initialize. We're just going to set it up. And so this is, we will calculate the speed of sound. Okay. What else do we need? Well, we had speed of sound, we had ping time, we need the distance. Okay, so we need that, and we probably can just make that an int because it'll probably, we better make that a float because that might be a, not a perfect round number, and so that is going to be target distance. Okay, and I'm going to go ahead and set that up here because I measure it, and when I measure it to be 6 inches. Okay, so we're going to go ahead and set that to 6 because we measured that with a ruler. You could set it to 12, but if you set it to 12, you would need to changes to 12. So you don't have to measure the speed of sound at 6 inches. It's just kind of a convenient thing because I got a 6-inch ruler. I can do that accurately. If you had a yardstick, you might want to do it for 36 inches. But I'm going to do it here for 6 inches because it makes it a little bit easier to keep on the camera here. I think that's pretty good for our variables. Down here, what do we do in void setup? We do the things that we want to do one time. What do we always want to do in the void setup? Turn on our serial ports. We're going to do a serial.begin, and we're going to set it to 9600. Okay, and we're going to turn on serial port. Okay, and then we're going to do pin mode. Okay, and then on the pin modes, we're going to have what? We have the trig pin. Well, we are writing to the trig pin. The Arduino is writing to the trig pin. So the trig pin is an output because we are writing to it. Set trig pin as an output. Okay. Pin mode. What's our other pin? Our echo pin. And the echo pin we're listening to, so we're reading from it. So the echo pin is an input. Okay, you've got to make sure that you're doing your input and output pins and your pin modes right. Set echo pin as an input. Okay, we've started our serial monitor. We've done our pin modes. I think that that's pretty much what we need to do here. Okay, so what do? Well, to make a measurement, we need to send a signal to the trigger pin, send it low, pause, send it high, pause, and send it low, pause, then run out and make our pulse in measurement. So we need to start by doing a digital write, and we go to our trig pin because we want to tell it that we want it to make a measurement. So we start by setting it low. And when you do these things, let's see, set trigger pin low. When you do these things, you always need to wait because remember the Arduino is really fast. So you got to stop and pause just a little bit to give it a chance to settle, to give that signal a chance to settle. So we're going to do a delay, and we don't have to delay very long. And if we just say delay, it delays in milliseconds or 1/1000th of a second. We want a small delay here, so we're going to do microseconds, and that is going to be in microseconds. And so we're going to delay 2000 microseconds, which would be 2 milliseconds. I guess we could have just said 2 milliseconds, but I wanted to introduce a new concept that you can delay in microseconds. Okay, so what are we going to do here? Pause to let signal settle. So we go down to low, and then we want to wait there just a little bit to give that signal a chance to settle out there. Okay, now we want to go high. Digital write, and we're going to go to the trig pin, and we're going to go high. So we set it low. Now we take it high. Take trig pin high. High. Okay. Now what do? We're going to delay microseconds. And you don't have to stay up at that pulse. You don't have to stay up at that tall pulse very long. You come up. You don't have to stay up there very long. You're just creating a trigger pulse. So probably 10 microseconds would be enough to keep it high. Okay. So we're going to pause. Pause with trigger pin high. So right, we set it high, and we're just going to wait there just a little bit to make sure the Arduino sees that it's up there. Okay, and now what are we going to do? We're going to bring it low. So we're going to digital write. Okay, and we're going to take the trig pin. We're going to take it low. Okay. So this sort of finishes the pulse. Finish trigger pulse by bringing it low. So do you see what we did? We just made a pulse at that pin 13. The sensors will see that pulse and it knows, okay, I need to send out the ping. I hope that makes sense. All right. So we've triggered this sensor. We've triggered the sensor. What do we have to do now? We got to go listen for that pulse to come in on the echo pin. And the width of that pulse tells us how long it took for the ping to go out to the target and come back. Okay, to go out to the target and come back. So how do we measure that ping? Well, we're going to say ping, and did I set up a ping time up here? Yes, I did set up a variable ping time. We're going to measure it, and how do we measure it? We measure it with the pulse in command, and this is going out to that echo pin, and it's listening for that pulse and seeing how big it is. So where are we going to listen for the pulse and do the pulse in? At the we got to tell it that echo pin. And then what are we looking for? We are looking for a high pulse because this sensor sends out a high pulse. And this will come back, okay? What will this do? It will measure the ping travel time in microseconds. So this tells us how long in microseconds that it took the ping to go from the sensor out to the target and to return. So now we've got the time, okay? So we've got the time, we've got this time, and we've got this distance. So what can we calculate? The speed of sound. So what we're going to have to do is we're going to have to say speed of sound is equal to what? What were our variables? Our distance was target distance. T-A-R-G-E-T, distance. Okay, but what you got to see is that if you look down here, if I am 6 inches, from the sensor to the target, what is the travel distance of the ping? How far did the ping go? Well, what you're obviously going to say is 6 inches, but what you got to see is the ping had to go from the sensor to the target and come back. So how far did that ping go? It went 12 inches. It went 2 times the target distance because it had to go there and it had to come back. It had to make a trip there and a trip back. So when we calculate the speed of sound, it's not the target distance. That's not how far the ping went. The ping went to the target and back. So it traveled a total distance of 2 times the target distance. And I hope that makes sense. Okay, and then we divide by what? We divide by the ping time. Okay, and what is this going to give? This is going to gives us speed in what units? Well, the distance was in inches, so the speed is going to be in inches per, what was the time in? It was in microseconds, so it's going to be inches per microseconds. Okay. So here we've calculated the speed of sound, but here's the problem. That's a correct answer, but it's not a very useful answer because people never think of things in terms of inches per microsecond. What you really want is you want miles per hour. And how do you do that? Well, let's come back up here to our lesson, and we'll just kind of go through this. What you have to do is you have to do what's called dimensional analysis. And dimensional analysis is where you go from one set of units to another set of units. So what do we have here? We have the speed in what units? In inches per microsecond. Okay, we have it in inches per microsecond. What do we want it in? We want it in miles per hour. So what we have to do is we have to multiply it by a series of basically things that equal 1. And then we can convert it over to the units that we want. So we don't want inches. What do we want? We want miles. Okay. Well, how do we take this to miles? Well, if I have inches up here, what I would want to say is 1 inch down here, because I want that inch to cancel that inch. 1 inch is, I want it in miles, so I come up here and I say 1 mile is equal to how many inches? Well, I can look that up over here on Google, and I can say inches in a mile, and what it tells me is 1 mile is 63,360 inches. So I can come back over here and you can see I already did it there, but this is going to be 63,360. So 1 mile is equal to 63,360 inches. Okay, and now when I come in, inches are going to cancel, and I got miles now per microsecond. But what do I want? I don't want miles per microsecond. I want miles per hour. So what do I know? Well, I know that 1 second down here, 1 second is equal to 1 million microseconds. Okay, so now that microseconds is going to cancel that microseconds. And so now I have miles per second. Okay, but I want miles per second, I want miles per hour. So what do I have to do? I know that 1 hour is equal to 3,600 seconds. Okay, so how is this going to work now? The inch cancels the inch, the microseconds cancels the microseconds, the second cancels the second, and now I have miles per hour. But I'm still multiplying by 3,600, multiplying by 1,000,000, and dividing by 6360. Okay, so that's the conversion that we're going to have to do. And I probably should do a video just separately on unit conversion so you can see that a little bit clearer. But here you're just going to have to kind of go with me on this one. And so let's call our program back up and see if we can get it here. Here it is. Okay, this is it. So here what we said is the speed of sound is 2 times the target distance divided by the ping time, and this gives us the speed in inches per microsecond. So now let's convert that. So we're going to say speed of sound is equal to speed of sound, and again what it was up here was in inches per microseconds. And so what did we need to do here? We needed to divide this by what? Divide it by 6360, because there's 6360 inches in a mile. So we divide by 63,360. Okay, now we multiply by what? We multiply by 1,000,000. Because there are 1,000,000 microseconds in a second. Now what do? We multiply by 3,600 because there's 3,600 seconds in an hour times 3,600, and this gives us speed of sound in miles per hour. Okay, so I hope that makes sense to you. Now what do we want to do? We probably ought to print out our results. So we're going to say serial.print, and we'll print a string. The speed of sound is, okay, serial.print, and then what was the variable? Speed of sound as a variable. Okay, and then serial.print line, because we're going to finish it up here, and that is in the string miles per hour. And you should know this now, all this printing stuff from the earlier lessons. Okay, I think that looks good. Let's send it down and see what. Oh, pause with trigger pin high. I forgot my semicolon there. Okay, let's see what else. I forgot a lot of semicolons here. I got in a big old hurry and I was not being careful. I think we're in good shape now. Still does not like it. Still missing one. I just had just a big huge batch of not putting my semicolons in. Okay, let's take a look. Hopefully you catch that. When I do that, hopefully you're sitting there yelling at me, put your semicolons in. Okay, so now let's come up and let's get our serial monitor. Okay, and this is going way too fast. So let's delay it here. Let's put a delay in. So let's just say delay. Let's put in like 3,000 seconds. I mean 3,000 milliseconds, which would be 3 seconds. Okay, so that it slows our measurements down a little bit. (786 miles per hour), 786 miles per hour. At 77 degrees, what would we expect the speed of sound to be? We would expect it to be 776 miles per hour, and we are getting 781 miles per hour. That's like 20 out of 1,000. That's like a 1%. We're measuring this to 1% accuracy, which is pretty incredible that for a $10 component, and what has it been, about 15 minutes of work, we are measuring the speed of sound very, very, very accurately. Probably the error is how accurately I measure the 6 inches. Probably that sensor is just dead on to the microsecond. Probably measuring that distance more accurately would give us a more accurate measurement. It might also give us a more accurate measurement if we went out to a foot or two in distance, so that we had a little bit longer signal, maybe a little bit more accuracy there, maybe a little bit more, a little bit easier to read. But anyway, I think that's great, and I think we had a good day today. What I want you to do is I want you to play around with this, play around with different distances, maybe like measure it at 6 inches, at 12 inches, and at 18 inches. Create a linear equation. In that case, if you're plotting distance versus time, the slope of the distance versus time would be rate. And so you could go in and you could kind of calculate the slope of that line, and you could back the speed of sound off that way. But I want you to show me that you've kind of taken this and gone somewhere else with it, and I will come around tomorrow for a daily grade on this, and just show me that you have got the measurement working, and that you've thought about it, and you've sort of taken this in a little bit new and different direction. Okay, again, Paul McWhorter, toptechboy.com. This is lesson number 17. Hopefully you will tune in very shortly for lesson number 18.